What's going on, guys? Justin here, and welcome back to our 14th example video following our course on abstract algebra. Now, all of the examples we're going to be doing today are going to be on the first isomorphism theorem of groups. So with that introduction out of the way, let's go ahead and get into our first example here. So for our first example, we have the following. We have if G is an abelian group and we have some natural number n, we want to show that the function phi, which maps G to itself, which is defined by mapping G to the n, is a group homomorphism. So if you recall, what we want to show to prove that this is a group homomorphism is that if we apply phi to two elements, let's just say A and B, that will be equal to phi of A times phi of B. Is that the definition of a homomorphism there? Great. So with that in mind, let's go ahead and apply that to this example. So we're going to go ahead and suppose that we have two elements. Let's just call them A and B, just like I did above, and they are going to be in our group G here. Then we want to consider phi of AB. So phi of AB. Well, applying our function to that is going to give us the following. We'll just have AB to the nth power, just like that. And then, of course, that's going to be equal to A to the nth times B to the nth, which is just equal to phi of A times phi of B, as that is the exact definition of what it means to apply phi to A and phi to B. Great. So that's just a quick little proof to demonstrate how to prove something is a homomorphism, and we're going to be using this a lot as we go through the next couple examples. So let's go ahead and get into our second one. So this one is going to deal with relations and equivalence relations a little bit, and we're going to suppose that phi goes from G1 to G2, and it is a homomorphism. And we're going to define a relation on G1 by A is related to B if and only if phi of A is equal to phi of B. We want to show that this is an equivalence relation. Now I want you to recall that in order to prove that this is an equivalence relation, we must prove a couple things. And those are that it is both reflexive, symmetric, and transitive. So let's go ahead and get into the reflexivity proof first. So we want to prove that this thing is reflexive, which is usually pretty self-evident, so let's go ahead and look at that. Well, we want to prove that A is related to itself, and A is related to itself if phi of A is equal to phi of A. But that is, of course, given by the fact that our phi is a homomorphism, so since phi of A is equal to phi of A, we know then that A must be related to itself, and thus this relation is in fact an equivalence relation. So next we're going to go ahead and prove that this is a symmetric relation. So let me go ahead and write out that we are doing symmetry now. So for this one, we just want to prove that if A is related to B, that means that B is related to A, which may not necessarily be the case depending on the kind of relation you are working with. So let's start by supposing that A is related to B, and then we'll just try and get to that B is related to A. Well, by using the definition of this relation, that means that phi of A is equal to phi of B. But of course, homomorphisms are symmetric, so that means that phi of B is equal to phi of A, or rather just by the definition of equality. And that, of course, using the definition of our relation here, means that B is related to A. So that's another quick proof done. So all we have to do now is prove that this relation is transitive, and we will have proved that this is an equivalence relation. So I'll go ahead and write that we are doing a transitivity proof now. Great, so for transitivity, it should be a pretty simple setup. We're going to suppose that we have that A is related to B, and also that B is related to C. And of course, because we're trying to prove transitivity here, we're going to try to prove that A is related to C. So let's go ahead and just break this down by definition. So that will mean that phi of A is equal to phi of B, but also it will mean that phi of B is equal to phi of C. And like I said, by definition of equality there, we can obviously see that that then means that phi of A must be equal to phi of C. Great. So these are pretty self-evident proofs, I would say, but just a cool little result there before we get into our next example. So let's go ahead and jump to that one now. So this example is treading more into the territory of what we would come to expect when we're doing problems involving the first isomorphism theorem of groups. And that result was proven in the lecture video corresponding to this example video, so make sure to check that out if you haven't seen it. Anyway, so this example says, suppose that phi is a function which goes from z50 to z15 such that phi of 7 is equal to 6. Then we want to find generally phi of n for any arbitrary n in Z50, and then we also want to find the image as well as the kernel. So let's kind of take this one piece at a time. Let's first try to find the general action that this phi does, using our example there that phi of 7 is equal to 6. So using exactly what we've been given here, we have that phi of 7 is equal to 6. But that means that we have that 7 times phi of 1 is congruent to 6 mod 15 by the fact that we're working in Z15 here. But we can use this to solve for phi of 1 as a simple linear congruence, which if you've taken a number theory class should seem pretty familiar. And we'll go ahead and write that in the following way, where we have 7m is congruent to 6 mod 15. Keeping in mind that this m is living in Z15. And the solution to that is given by m is equal to 3, which then gives us all the pieces we need to find our phi of n for an arbitrary n in Z50. So what this m being equal to 3 really tells us is that phi of 1 is equal to 3. And what we want to find is phi of n for some arbitrary n in Z50. So what that tells us is, well, let's consider phi of n. So if we have phi of n, well, that will simply be equal to phi of 1 times n. But we can pull that n out front, and we will simply get n times phi of 1, which we know to be 3, which is simply equal to 3n. So you can see that for any arbitrary n in Z50, phi of n will just be equal to 3 times n. So now that we found phi for an arbitrary n in Z50, let's go ahead and take a look at the image as well as the kernel so we can finish this problem off. So to use this, let's go ahead and break this down into the exact definition of what it means to be in the image of phi here, and we're going to denote that as Im of phi. Great, so everything in the image of phi is going to be in the following form, and that is all phi of n, which is in Z15, such that n is in Z50. And so since we've already found our phi of n here, we can make a simple substitution here. So what's going to be in the image of phi is simply going to be, so it's going to be all things of the form 3n, which is in Z15, such that our n is coming from the set Z50. But we can see the only multiples of 3 that are going to live in our Z15 here are going to be just multiples of 3 mod 15, which would be 0, 3, 6, 9, and 12. And of course, if we do another multiple of 3, we will go right back to 0. And this is, of course, isomorphic to Z5. Great, so that is our image for phi. So now let's go ahead and take a look at the kernel, and we'll finish this problem off. So once again, when we're talking about the kernel, we're going to start off by breaking it down by the definition, and so we want to talk about what it means for something to be in the kernel of phi. That's going to be every n which lives in Z50, such that we have the following relationship where n is congruent to 0 mod 15. Great. So that's just generally what this problem would be, but we've actually already done a little work on this. So in this particular example, that means it's going to be all n in Z50, such that 3n is congruent to 0 mod 15. So now we have to ask ourselves is what n in Z50 can we plug into this congruence to make it true? And the result is going to be all multiples of 5 in Z50. So the kernel of phi is simply going to be equal to all the multiples of 5, starting from 0 and going all the way up to 45. So I'll go ahead and abbreviate like this. We'll have 0, 5, 10, and I think you've got the idea, all the way up to 45. Now all we need to do is count these, and there are in fact 10 of them. So that means this will be isomorphic to Z10. Great. So we can see we found all of the elements which give us the identity in our domain. So that gives us the exact definition for our kernel in this case. So let's go ahead and get into our next example. So for this one, we want to consider the following, where we've defined a phi which comes from the group of reals with the operation of addition, and it is mapped to GL2 with real inputs, which has the operation of multiplication, and it's given by phi of x is equal to the following 2 by 2 matrix, where we have the entries as follows. We have cosine of 2 pi x minus sine of 2 pi x, sine of 2 pi x, and cosine of 2 pi x. So first we want to show that this is a homomorphism, and then we want to find its kernel. So let's start by proving that this is a homomorphism. So just like we did in the very first problem of this example video, we need to make sure that phi of, well in this case it would be x plus y, is equal to phi of x times phi of y. Great. So let's go ahead and look at that now. So phi of x plus y, as this x plus y is happening in our group R there, which has the operation of addition, that's going to be equal to the following, where we'll simply replace each x in this matrix with x plus y. Great. So that should be pretty straightforward. We will have the cosine of 2 pi times x plus y. Then we'll have minus sine of 2 pi times x plus y. Then we'll have here for our next entry, sine of 2 pi times x plus y. And then lastly, we'll have cosine of 2 pi times x plus y. So we want to show that this is equal to phi of x times phi of y. Great. So let's go ahead and see, well, what is phi of x times phi of y? It's a lot easier for us to calculate what phi of x times phi of y is than try to manipulate this into something that would resemble it. So let's go ahead and I'll write the question that I just asked. What is phi of x times phi of y? Well, we can figure that out by just writing it down from definition here. So that will be the cosine of 2 pi x, then minus sine 2 pi x. Then we'll have sine 2 pi x, and then lastly cosine 2 pi x. Sorry for my messy handwriting. And then we'll have phi of y, which will be given by cosine of 2 pi y. We'll have minus sine of 2 pi y. Then here we'll have sine of 2 pi y. And then lastly, we'll have cosine of 2 pi y. Great. So we're going to do this just using basic matrix multiplication. We are going to swivel the row of this first matrix into the first column of the second matrix. So let's go ahead and see what we get for the resulting matrix after those multiplications there. So we will have the cosine of 2 pi times x times the cosine of 2 pi times y, and that will be minus the sine of 2 pi x times the sine of 2 pi y. But we can actually combine this whole entry here using a sum angle formula, and that says that this whole thing will be equal to the cosine of our 2 pi x plus 2 pi y. So let's go ahead and write that down. That will give us for this whole entry the cosine of 2 pi x plus 2 pi y. Great. And so similarly, we'll swivel this first row into this second column here, and that will give us the cosine of 2 pi x times negative the sine of 2 pi y, and then we'll have negative the sine, and we'll have negative sine of 2 pi x times the cosine of 2 pi y. And using the sum angle formula, we will get negative the sine of 2 pi x plus 2 pi y. And similarly, the rest of these will follow by sum angle formulas and give us exactly what we have written up here. So that will give us the sine of 2 pi x plus 2 pi y. And then lastly, for this last entry, we'll have the cosine of 2 pi x plus 2 pi y once again. So like I said, through this matrix multiplication and by applying these sum angle formulas, we find that phi of x plus y is equal to phi of x times phi of y. So now we want to look at the kernel for this function here. And so the kernel is simply going to be, we have to have the following conditions be the case because we want to have an input from our x that will give us the identity in our GL2, which is the 2x2 identity matrix, which will have 1 on the diagonals and 0 on the off diagonals. So I'll go ahead and write that down. We want to find, so we need all x such that the following conditions are true. The first would be that the cosine of 2 pi x is equal to 1. And we also need that negative the sine of 2 pi x is equal to 0. Great. So where is the cosine equal to 1 and the sine equal to 0? Well, that will be at 2 pi intervals, or when x is equal to any integer. As any integer multiple of 2 pi will put us the same place on the unit circle and give us a cosine of 1 and a sine of 0. So our kernel of our phi in this case will be equal to the integers. Great. So that finishes this problem off. So let's go ahead and get into the next one. So for this one, we are given a group G, and they have given us a definition for an inner automorphism, which we haven't explicitly talked about in the lecture videos, but it is defined for you here. So an inner automorphism is a function which we've called psi sub G, which goes from G to itself, such that psi sub G of x is equal to this conjugation action by G, where we have Gx G inverse. So we have three things we want to show here. The first is that we want to show that psi sub G is an isomorphism. For number two, we want to show that this intermorphism thing is in fact a group. So we want to show that the intermorphism acting on G for all little g in G is a group. And then lastly, we want to combine 1 and 2 to use the first isomorphism theorem to show that the quotient group of G in the center of G is isomorphic to the inner automorphism group on our parent group G. So to start off, let's go ahead and prove that psi is an isomorphism. So I'll go ahead and write that we're doing that first. And if we're going to prove that it's an isomorphism, we have to prove two things. First, that it is a homomorphism, and second, that it is a bijection. So we're going to prove that it is a homomorphism first, which is something we've already done plenty of times in this video. So let's go ahead and write out that we're doing our proof for the homomorphism. So just like we've always been doing, we're going to take two elements from our group here. Let's call them X and Y, and we're going to take them from our group G. And then we want to consider psi of XY, and then see if that is in fact equal to psi of X times psi of Y. So let's go ahead and consider psi of X times Y here. That is simply equal to our X and Y conjugated by this relationship that we've been given at the top here. So that will be equal to G times XY times G inverse. And now we have to show that this is equal to Gx G inverse times Gy G inverse. But we can do that using a creative way to multiply by the identity in the middle of our X and Y here. So this is simply going to be equal to G times X, and then our creative use of the identity is going to come in here, where we'll write G inverse times G, and that is of course equal to the identity, so we are not changing the value of this expression here, and that will be times Y times G inverse. And you can see here we have Gy G inverse, and here we have Gx G inverse, so this will of course be equal to psi of X times psi of Y, which is all that we needed to show to prove that this is in fact a homomorphism. So now what we have to do is prove that this is a bijection to prove that we have an isomorphism here. So let's start off by proving that this is in fact an injection. So I'll go ahead and write that we are doing our injectivity proof here. So to prove that it's injective, we've done plenty of these proofs before. And actually in the lecture video, Michael outlined a way to prove that a function is injective using the fact that you can prove that the kernel is trivial to prove it's injective. But I'm going to be using a more standard injective proof here because I think it's pretty easy. So I'm going to go ahead and take two elements once again from our parent group G. Let's just call them X and Y again for simplicity's sake. And we're going to have it such that psi of X is equal to psi of Y. And we want to show that the fact that psi of X is equal to psi of Y then proves that X must be equal to Y. So let's go ahead and look at that. So if psi of X is equal to psi of Y, we can break this down using the definition of psi here. That means that Gx G inverse is equal to Gy G inverse. And this will be pretty easy to show, as we can multiply by G to cancel out our G inverses, and that will give us simply Gx is equal to Gy, and then we can left multiply by G inverse, and that will simply give us that X is equal to Y, which is exactly what we wanted to prove to show that this thing is injective. Great. So now all we have to do is prove surjectivity, and we will have proved that we have an isomorphism, which is the first part that we wanted to prove for this example here. So let's go ahead and get into our proof of surjectivity here, and that is we want to show that all of the elements of our codomain here can be mapped to. So let's go ahead and take a look at that. Well, if you'll remember, this inner automorphism is a function on G back to itself. So we have to show that we can map to every single element of G using our function psi here. So let's go ahead and take an element, let's just call it X, from our group G, and then we want to note the following to show that we can map to an arbitrary element of our group G. So I want to note that psi of the following will give us X, and that is, if you'll recall, the conjugation action that we've been given here is Gx G inverse. So if we take psi of G inverse Xg, which we can do as G is also an element of psi, then when we apply psi to G inverse Xg, we'll simply get G times G inverse Xg, and then a G inverse here by our conjugation action, but we can see that each of these G's will cancel, and we will simply get X. So here I've demonstrated that no matter what element we pick from our group arbitrarily X, we can in fact map to it with our function psi. Great. So the combination of these three proofs here is enough to show that this psi is in fact an isomorphism. is in fact an isomorphism. So let's go ahead and move on to our second proof, which is to show that the inner automorphism of G is in fact a group. Great. And so the proof of the fact that this is a group is going to be fairly straightforward. Given that this is an automorphism, we are working within the group, so we're going to have a lot that is inherited here. So normally when you are proving something as a group, you have a lot to prove. You'd have to prove associativity, you'd have to prove that there's an identity, and you have to prove closure. But the three things I just said are actually inherited from our parent group. We have associativity from the fact that our group, as the operation is preserved, we have the identity, which is maintained from the group because we're still dealing with all elements from the same group G. And once again, our closure is guaranteed because of this conjugation action is simply applying our operation between groups of G. So that is also a given. So all we have to do is prove that we have inverses to show that this is a group here. And so to demonstrate that we have inverses here, I want you to note the following, and that is that for all little g in our group big G, we have the following inverse. So we have that the inverse of G times X times G inverse is simply equal to Gx inverse times G inverse. And we can write the inverses like this because we know that Gx and G inverse are all members of our group big G, and since that itself is a group, it must have inverses. So we can see that this is in fact a proper inverse, as if we multiply Gx G inverse times G X inverse G inverse. We will have cancellation from the middle. This G inverse will cancel the G, the X inverse will cancel the X, and we'll have this G inverse cancels this G, and that will simply give us the identity element. So since we have inverses and the rest is inherited, our group of intermorphisms on G must be a group. Great, so that means we only have one thing left to show, and that is we want to use the first isomorphism group to put all these pieces together to show that the quotient group of G and the center of G is isomorphic to the intermorphism group of G. Great, so let's go ahead and get into that. So in order to apply the first isomorphism theorem to the quotient group of G in the center of G, we must first find a homomorphism between G and the intermorphisms on G. So let's go ahead and define a function that will serve as our homomorphism here. And we're not going to use too much imagination on this. So we're going to let phi, which will be a function from G to the intermorphisms of G, be defined in the following way, where phi of x is equal to the following. It will be equal to G inverse times x times G. Great. And now all we have to do is show that this is in fact a homomorphism, and we're going to do that just the way we have been doing all video. So then we're going to go ahead and consider the following. So we're going to consider phi of x, y. Well, if you remember what we did for our homomorphism above, it'll be exactly the same thing. So we'll have that this is equal to G inverse times xy times G, and just like before, we can multiply by a creative use of the identity here. This will be equal to G inverse times X, and then we'll write the identity in between where this is G inverse, and then we'll have Y and G, and just like we did before, this will be equal to phi of X times phi of y. So we do in fact have a homomorphism here. So now we want to look at the image to show that the image is the intermorphism of G. And then lastly, if we can show that the kernel of G is equal to the center of G, we will have done all we needed to do to show that we have the quotient group of G and the center of G is isomorphic to the intermorphism of G by the first isomorphism theorem. Great. So let's go ahead and look at the image next. Well, there's not much to take a look at here, as by construction, it's very clear that the image of our function phi here is simply equal to the intermorphisms of G, just by the way that we constructed it. So now all we have to do is show that the kernel is equal to the center of G, and we will be done here. So let's go ahead and write that out, that we are looking at the kernel next. So for the kernel, what we want to do is we want to find all x which are in our group G such that phi of x is equal to x. Well, let's go ahead and apply our definition of phi here and see when those cases may be. Well, phi of x is simply equal to G inverse times x times G, and we want that to be equal to x. But we can left multiply by G here, and then we will get xg is equal to gx. But when is xg equal to gx? That is when x is a member of the center of our group G here, as it commutes with every arbitrary element little g in the group. Great. So we found that the kernel is the center of G, and we found that the image of our function phi, which is a homomorphism, is equal to the intermorphisms of G. Thus, by the first isomorphism theorem of groups, we have that G mod out the center of G must be isomorphic to the intermorphisms on G. Great. So that finishes this problem off, and let's get into our last problem for the day. So for our last problem of the day, we're going to let R be the additive group of real numbers. We're going to write R superscripted X be the multiplicative group of non-zero real numbers, and then we're going to let R sub plus and superscript X be the multiplicative group of positive real numbers. So we have three things to prove here, or really only two, and that is, first, we want to show that R is isomorphic to the multiplicative group of positive real numbers using the map X is mapped to e to the X. Then we want to show that the multiplicative group of non-zero real numbers mod out the set -1, 1 is isomorphic to the multiplicative group of positive real numbers using the first isomorphism theorem, with the map X is mapped to the absolute value of X. And then lastly, once we have done that, we can conclude that the multiplicative group of non-zero real numbers mod out the set -1, 1 is in fact isomorphic to the additive group of real numbers, just using basic transitivity there. Great, so let's go ahead and start with this first thing so we can wrap this video up. So first we want to show that R is isomorphic to the multiplicative group of positive real numbers, and we're going to use the map X is mapped to e to the X. Well, in order to show that it's isomorphic, we first have to show that that map is in fact a homomorphism, and then we just need to show that it is a bijective map. So let's start and do the proof that it is a homomorphism first. So let me go ahead and write that out for you here. We're going to be doing a homomorphism proof. And so to do this, we're going to keep doing what we've been doing. We're going to take two elements from our domain, let's call them A and B, and they're going to be in our additive real number group here. And we want to consider our function acting on those together. So we want to consider phi of A plus B. Well, just applying phi to A plus B, that is simply going to give us e to the A plus B, but then using exponent rules, we can split that up as e to the A times e to the B, but that's exactly what it means to be equal to phi of A times phi of B, using the definition of our map there. Great. So now that we've proved that this is a homomorphism, let's go ahead and get into our injectivity proof here. Now, I'm going to be doing just a standard injectivity proof here because I think it's pretty simple. So let's go ahead and suppose that we have X and Y, which are in our domain R. And we'll have that we will have chosen our X and Y such that phi of X is equal to phi of Y. And we want to show that that means that X is equal to Y. That's fairly straightforward, as phi of X is simply equal to e to the X, and phi of Y is simply equal to e to the Y. And if we have e to the X is equal to e to the Y, then we must have that X is equal to Y, and that completes the proof that this is injective here. Great. So now all we have left to do to prove that this is in fact an isomorphism is to prove that we have surjectivity. So let me go ahead and write that out. We have surjectivity, and that is we want to show that we can map to every single element of our codomain here. And in this particular case, our codomain will be the multiplicative group of positive real numbers. So that is to say, we want to prove that we can choose some element from the reals and show that we can map to it. Great, so I'll go ahead and write that. Let's go ahead and take some element, let's just call it n, from our codomain, and I want to show that we can map to that element n. Great. Well, I want you to go ahead and note the following, and that is that if we apply phi to the natural log of n, we will get n. So phi of the natural log of n is simply equal to e to the power of the natural log of n, but that is just equal to n. So for any positive real number, we can map to it using our function, which means this function is surjective, and combined with our injectivity proof and our homomorphism proof, we have proved that this map is in fact an isomorphic map. So R is isomorphic to the multiplicative group of positive real numbers. Great. So for the second one, we're going to want to use the first isomorphism theorem to show that the multiplicative group of non-zero real numbers mod out the set -1, 1 is isomorphic to the multiplicative group of positive real numbers using the first isomorphism theorem, and the map X is mapped to the absolute value of X. Well, we've already done some of these, so let's go ahead and jump right into it. So first we want to prove that this map is in fact a homomorphism, and we're going to do that just the way we have been doing. So let's go ahead and jump right into the proof. So let's go ahead and suppose that we have an A and a B in our domain, which in this case will be the group of non-zero multiplicative reals. So, and then we want to consider phi of AB. Well, in this case, our operation is multiplication, so we want to consider phi of A times B. Now, if you recall, phi maps A to the absolute value of A, so this will be equal to the absolute value of A times B, but that is equal to the absolute value of A times the absolute value of B, which we can split up like that, but that's simply equal to phi of A times phi of B. Great. So that proves that we have a homomorphism here. So now we want to look at the image as well as the kernel to apply the first isomorphism theorem. So first, let's look at the image here. Well, it's pretty obvious what the image of this is, as given the fact that we are working with the absolute value of here, the image of our function phi is simply going to be equal to the positive real numbers, or r plus. But that's exactly what we wanted to show for the image. So we are done there. Now all we have to do is look at the kernel. And that is to say we want to know what elements we can feed into our function phi that will give us the identity in our codomain, which is the multiplicative group of positive real numbers. Well, the identity in that group is equal to 1. So what can we plug into the absolute value to get 1? Well, that is 1 and -1. So the kernel of our function phi here is simply equal to the group -1 and 1. And so you can see here from these two results, we can now apply the first isomorphism theorem for groups. And we will find that the group Rx mod out our kernel, which is -1, 1, is simply equal to our multiplicative group of positive real numbers here. Great. Or I should say isomorphic. So now we can combine these results. Well, let's see, what did we prove so far? Well, we've proven that the additive group of reals is isomorphic to the multiplicative group of positive real numbers, and we've proven that that multiplicative group of positive real numbers is isomorphic to the multiplicative group of non-zero real numbers, mod out the set -1, 1. So by transitivity, we will have the following, and that is that R is isomorphic to this quotient group we just found here, and that is the multiplicative group of non-zero reals, mod out -1 and 1. Great. So that finishes this last problem off, and that's a good place to stop.